Hello students, welcome to this lecture number 4 on state of matters. In this lecture we are going to discuss the ideal gas equation. In the previous 3 lectures, what we have discussed, let us have some recap of those lectures. First lecture that we have discussed about the different types of intermolecular forces and how the state of the matter has been varied, means why there is a 3 state of matters, that is there is a solid state, liquid state and gaseous state, that we have discussed. In the second lecture we have discussed about the 2 important gaseous law, that is Boyle's law and Charles law. And the third lecture we have discussed again 2 important gaseous law, that is the Avogadro law and the Avogadro law. So in this lecture, that is lecture number 4, we are going to discuss the ideal gas equation. Ideal gas equation that we are going to discuss in today's lecture. And this is K.K. Mukherjee, the Science with Mukherjee Sir YouTube channel. First, let us understand what do we mean by ideal gas. Ideal gas is such a gas which strictly follow the Boyle's law, Charles law or Avogadro laws. And actual ideal gas, if you see that it is a hypothetical one, imaginary, because in ideal gas it has been considered that there is no intermolecular force of attraction. And another gas, that is the real gas. Real gas is such a gas which follow the ideal gas law, that is Boyle's law, Charles law and all those laws that we have discussed in our previous 2 lectures, that will going to follow in some special circumstances, in special conditions, and beyond that conditions, any other condition, it will not going to follow the ideal gas law. This is called the real gas. We will discuss about this in the special why there is a deviation from the ideal gas law and the real gas has been established. How we can going to discuss. Now we are going to discuss the ideal gas equation. What is that? It is basically when we combine the 3 important gas law, that is Charles law, Boyle's law and Avogadro's law into one, it will going to give us the ideal gas equation. So let us understand, let us formulate this ideal gas equation. When we know these are 3 laws, that when temperature and amount of substance, that is the mole, is constant. Mole is constant. These are all the constant. Now we can write this is constant. When this is constant, then as per Boyle's law, volume is inversely proportional to the pressure. When pressure and amount of substance constant, then volume is directly proportional to the absolute temperature. And when pressure and temperature is constant, at that time volume is directly proportional to the amount of substance, that is Avogadro law. And these 3 laws, when we combine, it will going to give us this. When 3 laws has been combined, it will going to give us this, and when we are going to put this proportionally constant R, and it is going to give us this. And if we arrange this, it will looks like VV is equal to nRT. This is the very important law that we have to always use this law. This is the ideal gas equation. In this ideal gas equation, you can observe that there are basically 4 variables. These two, pressure, volume is variables, and you can see number of moles is a variables and temperature is also a variables. Here R is equal to a constant. So when we write R is equal to, this is called the gas constant, PV by NT. This is the constant, gas constant. It is also called the, because this constant is same for all the gases, and that is also called the universal gas constant. Universal gas constant. And you can understand this universal gas constant depend on the units, in which units were measured the pressure, which unit were measured the volume, and which units, that is the mole is there and the temperature is there. And depending on that, universal gas constant will vary. Now we understand that this, if we vary, that is the 4 variables is there in the gas constant ideal gas equation. If one of them variable, 3 of these variable we know this, because R is a constant, that is a constant term, then we can able to automatically able to say about the 4 number of variables. So suppose volume of 8 mole of gas, volume of 8 mole of gas at constant temperature and pressure. This is volume is equal to, we can easily able to derive, that is a N, that is for N mole of gas. So this will be so volume of the N mole of gas at constant temperature and pressure will be this. So you have to put the N also, and you can see that N mole of gas is a constant term, and that is what Avogadro says. So we can prove from this ideal gas equation the Avogadro law also. Now we are going to discuss another very important thing, that is how we can able to calculate the universal gas constant. So ideal gas equation, we can see it is basically a equation that will also going to represent the state of the gas. So this also called the equation of state. Ideal gas equation also called the equation of state, because it represents the different variables. It is consisting of the different variables, that is PV is equal to nRT. Here you can see P is one variable, V is one, N is one, and T is one. There is a 4 variables is available. So this will have this name, that is equation of state. For the ideal gas equation, it is also is very much helpful when we are going from the another state of the gas to the other state. Suppose the pressure, volume and temperature for the fixed amount of gas we are changing. Suppose initial condition was P1, V1 and T1, and it will be changed into P2, B2 and T2. Then for a fixed mole of gas, we can write NR, that is equal to P1 V1 by T1. And another case, because this is a fixed amount of gas, you can write P2 V2 by T2. Okay, So we can equate this P1 V1 by T1 is equal to P2 V2 by T2. And here you can see there is totally 6 variables are there. If we know the 5 variables, we can able to calculate the one or other. Okay, so this equation also called the combined gas law. This equation also called the combined gas law. So you understand what is the ideal gas equation? It is basically PV is equal to nRT, and it is also being named as equation of the state because it represents the state of the gas. And for the simultaneous changing of the variables from P1 V1 T1 to P2 V2 T2, it will have this equation and it is called the combined gas law. The R is basically, you know, PV by N into T. So when there is a STP means standard temperature condition, where the temperature is 273.15, pressure is 1 bar, and at that temperature pressure, for 1 mole of gas, this will be 22.7 liter. So we can calculate R is equal to, we will just put this value here, that is 1 bar into 273.15. This is volume. We have to take the volume here, 222.7 divided by 273.15. So this will coming around 31, and its unit will be the bar liter per Kelvin per mole. This will be the units of this. Now we can change when this is also being changed like this, when we know 1 liter is equal to 10 to the power 3 meter cube and 1 bar is 10 to the power 5. We are changing the units. Here units was different. Now here we are putting these units. 1 liter equal to 10 to the power minus 3 meter cube and 1 bar equal to 10 to the power 5 Pascal, and this will be, if we put this value, ten to the power 5 so it will be coming around 3.1314 Pascal meter cube per Kelvin per mole. So you can see that when we changing the units of the pressure volume, the value of the universal gas constant is also changing, and this is also been written 3.14, that is joule per Kelvin per mole. So you can understand that how the universal constant is changing, value of the changing when we change the value of the units. And here we will see at STP, Now we see at NTP. NTP we know the temperature is 273.15, pressure is 1 atmosphere, and volume is here 22.41 liter. We will just put this R is equal to 1 into 22.4 divided by 273.15, right, and it will be coming around, if we calculate it, this. And when we change this into the liters or into the centimeter cube, that it will be changed. Suppose we know 1 liter is equal to 10 to the power 3 centimeter cube. So it will be coming around, this will be coming around 82.1 atmosphere centimeter cube per Kelvin per mole, and here one unit was there, atmosphere, liter atmosphere by Kelvin per mole. So what we see that universal gas constant is changing when we change the units, and this will be very much helpful when we are go for the calculations. Different type of numerical will come and unit will be different, and accordingly you have to put this universal gas constant. Okay, now we will do some numerical. Pure hydrogen sulfide is stored in a tank of 100 liter capacity at 20 degrees Celsius and 2 atmospheric pressure. The mass of the gas will be this. How do we calculate? We have to take the help of ideal gas equation. This is, and we know moles is equal to mass of the gas divided by molar mass. And what we have to calculate the mass of the gas. W we have to calculate. Now what is the M? First let us convert this, we have to equate this mass with this all other variables. Okay, now we will put this in here, W by M at. Then this will be W is equal to P B M by RT. Now M we know for H2S it is 34. Pressure is given here. Pressure is given here. What? 2 atmosphere pressure. Atmosphere pressure. Volume is given here 100 liters. Mass is, molecular mass is 34 of H2S, and we have to choose the R. R is in the liter atmosphere. Liter atmosphere we know that will be this value. This is very important. Sometimes it will be bar, that also you have to liter bar, that the units that you have to choose. And liter atmosphere this is, and T is given here. We have to convert it in the absolute temperature. It will be this. So if we equate this, we will find this answer will be 282.68 gram. That is, the C is the right answer. So in this way, this type of question will come, numerical will come, and we have to answer by taking the help of this. This is the second question, that container of A and B have same gas, pressure and volume and temperature. Of A are all twice of B, then the ratio of the number of the molecules of A and B are in this ratio. So for that, what we have to do, we have to basically we have to calculate the moles of the gas. Gas is our same gas. but its mole will be changed. So for calculating the mole, what we will do? We will know PV by RT. So mole in the, suppose mole in a container A is Na, and that will, you can say the volume, pressure is Pa, volume is PV, and R into TA. Moles into B container of the gas is PB VB by TB. So the ratio number of molecules is proportional to the moles. If the moles is higher, then number of molecules will be higher. So if we can know the moles, ratio of the moles, and that will be the molecules also. So we can write Na by Nb. You will straight away write this Pa Va by Ta. This will given Pa Va into Tb and we know that it is twice of the B. It is twice of the B. Means here you can write this here, that 2 Pb, because Pa is equal to Pb, 2 Pb, then 2 P Va, and it is also this, and here Pb into Vb and 2 this. So it will coming 2:1. So that will be the right answer. Okay. So the ratio of the molecules in the container A and container B will be 2:1, where the condition is totally twice of the container B. Okay. That is all for this today's lecture, and in this lecture we have discussed about the very important thing, that is the ideal gas equation, and this is very important for numerical point of view and theoretical point of view, and you must understand all the things. Hope you understand. That is all for today's lecture, and thank you very much for watching.